In this tutorial, you're going to learn, and you're going to do it yourself, NLP analysis of text passages to classify what is the subject of a certain piece of text using AI. And the library we're going to make use of is sklearn, which is one of the most popular used in machine learning in general. So just search for sklearn and click on it. And under tutorial, you want to click on down, working with text data. So here you have all of the code and all of the information that you need. And really, you should stop watching this video and go to that website if you really want to understand it. But I want to show you how to actually do it. So go to Colab in your browser, which is Google's free Jupyter Notebook application. Click on the bottom, Start New Notebook, and let's get started. So you can type along with me, make sure you're following, and we'll do one command at a time. We'll try to understand what's going on at each point. So first, hope it's big enough that you can see. First, just type in from scikit-learn datasets, import fetch 20 news groups, because the dataset we're going to be using is actually built into the scikit-learn library, and it's going to be based on stories that were collected in news and labeled based on their subject matter. So next, there's a bunch of categories. We don't want to use all 20. We're going to just use a few. So I typed in here baseball. You can do hockey also if you want. That's recreation, sport, baseball, science, medicine, science, electronics, and then computers, systems, IBM, PC, and hardware. Now, I just want to tell you why I'm choosing these subjects is because the confusion between different topics that a person might be most likely to make a mistake is not between baseball and the other subjects. That's pretty easy to distinguish. But let's say between electronics and hardware, that's a bit of a subtle distinction, even for a human being. So we might anticipate the computer is going to have a little bit of trouble with that. And even maybe between medicine and electronics, you know, machines in hospitals might involve electronics and they might involve medicine. So let's just anticipate that, and we'll see at the end whether there's less confusion between baseball and the other categories, and if there's more confusion between electronics and hardware. Now, the next command you want to type in is the following. I'll make a new cell. Just type in 20 train. This is going to be our data set. And forgot to click run here. I can press the play button like this, or I can just press shift enter. Same thing. Now, once I have my 4 categories, then I'm going to define my train data set, which is called 20 train, even though I'm only using 4 out of the 20, but it's going to be from fetch 20 news groups, which is the data set that we imported at the top, and which subset you're going to use the training set, not the test, as opposed to the testing set. And this is going to be the group that we're going to learn. Our model is going to learn and be fit upon. And the categories we're going to use those for that we defined above. Next, shuffle just means that we're going to randomize the order. We're not going to have them in a classified order because that might be, this will be to our advantage, the fact that we shuffled it. Generally, we want to train models. And a random state, just so we can reproduce errors, we choose any random number there, 42, be anything, just so that it's sort of a pseudo-random choice of a subsample of the order, and the shuffling of the order rather, that we'll be able to reproduce any results that might occur just by choosing that same random seed, random state. And once that's loading, we're going to put in our next command, which is just to look at a basic feature here. That is the length, len, is the length of the 20 train.file names. So the file names, that's a list of all the names that we have, and the length is going to be the number of files. So you see you have 2,000 plus files, which again contain subject, content, so on. Let's look at just a few features here that are important. The 20 train.target names is what we chose as the categories when we defined our input. So that's hardware, baseball, electronics, and medicine. Next, we are going to choose a random passage. I just chose as my passage index 62. You can pick any number. Then my passage index going to be subject index is going to be defined by the attribute of 20 train called target. So I'm going to type 20 train.target, which is going to be the sort of like the key code between the indices and the actual subjects. Then my passage index, that means the 60-second passage I'm going to use. And then finally, I'm going to use 20 train.target names in order to transfer between the number and the actual subject name. So my subject index, my passage index is going to be 62. And I just want you to see that. So let's just type my subject index first, just to get an idea of what's going on. So that means it's subject number 3. But we don't really want a number 3. That's kind of useless. So we're going to plug that in, my subject index, which is 3, into the key code for the target names. And we'll see that that is medicine. Now, next, let's look at that passage. So some information about it. Type in the following, that you should print. You're going to join a bunch of elements together with each one on a successive new line. So that's the /n and .join to put the items together in a string. And it's from 20 train.data from my passage index, which was 62. I can pick anything. And that will be split based on the new lines. We're going to take the first 3 rows. So let's press Shift Enter. And we get the first 3 lines, which are from Daniel Prince, and the subject is placebo effects, and it has 17 lines. So that's our sample passage that we're going to look at for a minute. What you want to do next is to look at what kind of vectorizers we have, because right now everything's in terms of words, but with the computer doesn't understand words, it only understands numbers. So we're going to need a vectorizer to convert the words into numbers. But before I do that, I just want to show you how you can see what the actual text is. Let's try looking at this. Okay, 20, type this. Next cell, 20 train.data, and use the my passage index, which we have the subject placebo effects. Let's look at the whole thing. So this is the article. I know the placebo effect is where blah 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 gets better or worse based on the blah blah blah, the doctor administering it. Okay, so that's the text, and we have the assigned subject. So let me comment that out for now. And the idea being, we're going to have a bunch of thousands of these passages, and we want to be able to correctly identify which subject does it belong to based on keywords. And instead of making rules to do that, we have the machine learning model just trained based on all the examples to determine which features or which words, frequencies, and which vocabulary most likely indicate that it belongs to, let's say, medicine versus baseball or the like. So what we're doing now is from scikit-learn feature extraction.text import count vectorizer, because that is going to count the number of words, and therefore when a keyword, let's say sickness or disease or remedy or pills or drugs, so those are going to be those keywords are going to be associated with medicine, whereas laptop, screen, keyboard, those are going to be associated with hardware. Or fastball, curveball, catcher, dugout, that's going to be associated with baseball. That's what we're doing by count vectorizer. We're counting. First, we're going to initialize the method, make an instance of the method countVect, and the more words the more times that the words that are associated with baseball occur, that will determine the subject. That's the assumption of this algorithm. Now, when you define X train counts, what we're doing is using that count vectorizer, and we're fitting it and transforming it. Now, the fitting, basically, in terms of statistics, you want the mean to be 0, so that things are not off center, and you also want the standard deviation to be 0, just to make things neat and normalized. So that's what the fit does, and the transform actually performs that change onto your training set, your training data. Again, well, the main thing that for us is we're transferring the words into numbers, and using that fine-tuning of statistics based on the fit. And this is important because we're only going to do this on the training set, the fit. But the transform, we're going to do on the training set and on the testing set, because you don't want to fit on your testing set, since the testing set is really supposed to be unseen examples. Now, the input is going to be 20 train.data. And we're going to look at the shape. Moment. The shape is 2,000. Well, this is the number of passages. If you remember that number, it's 2,372 passages. And then each passage has a certain number of features based on the words, their number of occurrences. When you add them all up, there are 33,378 number of features. That means basically the number of unique words that are going to be. Obviously, if you chose more passages, then you would have a larger number of unique words. But what we want to do next is following. Type in get, you want to get the vocabulary using countVect.vocabulary.get using this algorithm. And for that, we get 5,238. And maybe there will be an opportunity later to explain what that does. But what we want to focus on for this moment is the different methods of classifying or determining the features, the important features of a passage based on its term occurrences and term frequency specifically. So that's why we have next the sklearn.featureabstraction.text. We're going to import, instead of using count vectorizer, this time we're going to use TF-IDF transformer. What's the difference between count vectorizer and TF-IDF? The count vectorizer just takes the total number of occurrences of words, but that's not really, that doesn't really sound like it will be ideal, because it could be skewed and offset by the simple fact that, let's say you have an article which is 100 words long. So let's say 10 of the words have to do with baseball, so that's going to be 10%. Whereas if you have an article that's 500 words long, so if also 10% of the words have to do with baseball, so that's going to be 5 times more words. So you don't want that to get a higher score in terms of likelihood to be connected with baseball necessarily. Maybe it will be proportional, and maybe you want to only determine the subject based on the frequency, not the number of occurrences total. Therefore, you would just simply divide by the number of terms in the passage. That is one approach that sometimes is better. It doesn't always help, but a good idea to try. Intuitive. Now, we're going to instantiate the method of the TF transformer by using TF-IDF. We didn't discuss the IDF yet, just the TF, term frequency, as opposed to the total number of counts. The term frequency is the ratio of the count versus the, in other words, divided by the total number of words in the passage. But we're going to instantiate that transformer, and we're going to use IDF false. So that's because it's a more subtle trick we're going to only use later. So I want to do first things first. So TF transformer, you're going to fit that, just like we did with the previous model, to the X train counts. And then you're going to type in the train TF is the transformer that we just fit. Now you're going to transform it to convert the words into numbers, incorporating the statistics that you found from fit on the xtrain counts. Remember, xtrain counts is what we are defining based on the model, how it interpreted the data. So just a minute, I'm going to look where I defined xtrain counts. I see up here, xtrain counts is defined as the count vectorizer. Now let's use this instead. Try that. See what we get. Okay, it would appear that we need to use xtrain count that we calculated based on the transformer above. Fine. And again, the first number is the number of passages, and 33,000 is the number of features based on the number of unique words. And again, it's the same number that you got for the previous model, but it's a different algorithm because here we're dividing by the total number of words in the passage. Now, next step is to use a third method, and this is a little more subtle, and not just using the term frequency versus the total number of words. We're actually going to divide furthermore by the frequency of that passage in other documents. So we have CF IDF transformer like before. I mean, now we're going to set this parameter of use IDF to be true. And what does that mean? Words that are common to all articles, for example, words like said or reported or news, those are not those are common words in any article, but that doesn't dictate which subject they belong to. So we don't want to account for those. We want to divide them. We want to divide the term frequency, which means how important a word is in this article, by the total frequency that that word has over all documents. And that's why it's called inverse document frequency. So words like dugout or home team or fastball, those are going to be important. Whereas words like reported or news, which are going to be common in all articles, are going to be less important when it comes to classifying baseball, even though those words are very common in baseball as well. So we take xtrain counts and we use that to fit our instance of the transformer class. Then we transform it using the statistics to convert the words into numbers. And then we're going to look at the shape, and you can guess what the shape is, the same as what it always was, because we have 2,300 sentences or articles and 33,000 unique words. So that's the number of features. Because that's how we're determining the number of features here. It's just we don't care about the syntax and the order of words and anything deeper than that. We just want the number of occurrences or frequency of words. That's why it's called bag of words, in fact, because you don't care about the order. Now, one of the known algorithms that performs well on text classification is multinomial naive Bayes. And maybe at another opportunity we'll describe how that works. For now, we want to focus on using it from scikit-learn.naive Bayes. You want to import the multinomial naive Bayes, and you want to define the classifier. That's an instance of the class multinomial naive Bayes, and you're going to fit it. I'll separate this on another line because, just to make it clear what's happening, you want to instantiate the classifier, and you want to fit the classifier. That's the third line here, based on the train CF IDF. That's the vector. That's the number of words. That's the number of vectors that we got for the 2,000 plus sentences. And we have fit our model, and that was the learning stage. Now, what we want to do is make some predictions. So, for instance, docs new is a list of sentences that I put, just that I know what subject they belong to, but let's see how the computer performs at it. So the first sentence is null and Ryan express. So that's pretty clearly to do with baseball. And then my del is not working. That clearly has to do with the system PC for hardware. And then this patient needed a stint. That has to do with medicine. So let's see how the computer does in classifying those. So we're going to define x new counts, which is the count vectorizer transform method applied to these new documents. And then we're going to use that in the counts. We're going to transform using the TF-IDF transformer to basically divide by the term frequency in the document itself, as we explained above. And now we're going to make predictions, where the classifier CLF is, we're going to call the method to predict on the new TF-IDF for these three sentences, and we're going to see the results that we get. Let's see. Just press shift enter. So null and Ryan express is connected with baseball. My del is not working is connected with electronics, and the patient needed a stint is connected with science and medicine. So that looks actually pretty good so far. Let's see what else we can do. We can make this whole process a little more efficient by defining a pipeline. We're going to import from scikit-learn.pipeline. We're going to import pipeline, make the whole process a little more flowing. That's why they call it a pipeline. And you'll see, because we vectorized, we counted the words, we got the number of occurrences, and then we want to make the term frequency accounted for by dividing by how often that word occurs. In addition, often the inverse document frequency for those words that appear in all types of articles. And then we want to make the classifier and train it. So that is all made compact. Instead of doing it all separate steps, it's made compact using this pipeline. You see the different parts. That's built into the scikit-learn package. So now that we have our classifier called, and the result is going to be the classifier called text CLF. So we're going to press fit. We're going to make the model learn based on our training data. And what are these two things? The data, the 20 train data, that's the actual words of the articles. And the 20 train target, that is the labels that are associated with it, meaning the number that is associated with subject matter, with a category. So for example, the one that we looked at was an article from 20 train data about what was it? Placebo effect. And then the target is going to be the number that was the key code for the appropriate subject. So we're going to fit, and our model is going to learn now. And this result just shows you the steps. Because first we have the vectorizer, counting the term occurrences, unique words. And then you have the TF-IDF, which divides by term frequency, and furthermore, the inverse document frequency. And the classifier defined and now is trained upon the training data, the 2,300 passages. Now what we want to do is to see how we performed. So first, see, before we just tested it on 3 example passages. Now we're going to test it on thousands of passages. So we're going to import NumPy as NP. That's used for linear algebra and handling vectors that we're going to use frequently. And 20 test is going to be similar to the training set, but this is going to be the unseen testing set. Is going to be fetch 20 news groups. The subset this time is going to be test. The categories are going to be the 4 that we defined above, 3 or 4. And shuffle is going to be true because you don't want any bias based upon ordering, any rigging of the deck. The random state, we know we want to use that to reproduce any involved in our random choice of numbers. If in case we run into a bug, we want to always be able to reproduce it. Now, the documents test is going to be the test data. It's going to be the data, that's the articles from the 20 tests that we just defined above right here. And that will be input into the prediction method of the text classifier that we defined using our pipeline. And the output will be this predicted set of classification guesses or predicted labels for the passages in the prediction or the testing set. Now, we're going to use NumPy here, get the mean. Let's see what the result is. So, in other words, we're going to see how close were our predictions to the target, to the actual targets, to the true targets, true labels. And we see we got not a bad score. It's 92% score for the mean in terms of that's the accuracy measure that we're using. And now we can further do fine tuning, because 92 is good, but you can always get better. Well, let's see if we can get any better. We're going to use something called from sklearn, the linear model. We're going to import the SGD classifier, the stochastic gradient descent classifier. Now we're going to see how that performs. We're going to redefine text classifier as follows using the pipeline. The vectorizer is going to be the count vectorizer, and we're going to use TF-IDF as well. And the classifier is going to be, this is going to fine tune the procedure, not using the multinomial naive Bayes algorithm. We use a different algorithm of stochastic gradient descent, which basically is that's the way of reducing the error each time the classifier makes a guess on the training set and it makes a mistake. So it recorrects in the opposite direction of the error in terms of the vectors, the numbers that the words were converted to, and that's how we know how to improve our model to make better guesses. And it keeps doing that until it gets to hopefully the optimal choice. Now, let's just see all the parameters here. The loss function, you have to define what's considered the degree of how off your prediction was. That's defined by hinge. And then there's a penalty, talk about at another time. Alpha is the learning rate, so that's 1/1000th, 1 times 1 exponent minus 3. So that's the rate, that's the learning rate. How much of a correction backwards does the model make when it sees that it got something wrong? It was too far high, so how much does it go back low? If it was too far to the right, how far does it go left? And we're going to use a random state again. And we're going to use the max number of iterations that we'll talk about at another time, not here. Our tolerance of none, also that will be another opportunity to discuss. Now, the text classifier, we're going to fit it based on the articles in the training set using the target, which is the labels from that training set, correct categories. And then we're going to define predicted as our predictions based on the classifier that we just trained, and using the predict method on the document test, which is the testing set that we defined in the cells above. Now, finally, the NP mean, that's going to be our accuracy measure. We're going to see how well did we do. So we see that we get 92.77%. So let's compare that with the old one. That's a little bit better, not much better, but it's a little bit better than using multinomial naive Bayes. Okay, so we got to compare these two algorithms. And you might be wondering something, that this is just the overall score, but what if you want to know how well did the algorithm do on each individual category? So for that, we're going to use the built-in package in scikit-learn called metrics, and we're going to use the metrics classification report, meaning how well did it do on all the specific sections, and we're going to evaluate that on the predicted set. That's the predictions that we made, and the target names are going to be the target names from 20 tests. That's the testing set. Those are the known labels. So this is going to give us a rundown of all 4 categories: hardware, baseball, electronics, and medicine, that we want to see how well did each category do. And we're going to see not all categories might perform the same. Let's run that. What you get is this display. Let's just for instance, let's look at the F1 score, because that's a good way to account for both precision. It's the harmonic average between the precision and recall. So the precision means when it made a guess, how accurate was it? Meaning of the predictions made, how many were correct, percentage-wise. And the recall is of the correct answers out there, the correct labels out there, how many did we capture? So the F1 score tries to capture a little bit of both the truth in both of those figures by taking the harmonic average. And we see that hardware got a score of 92. Medicine actually got a score of 95. The highest score was baseball. And we might see that might be a reflection of the fact that baseball has really nothing to do with the other subjects. And the lowest score was 87. That's electronics. I would suggest maybe that electronics got a low score, perhaps because it's very related with hardware and with medicine, perhaps. Whereas those two, hardware and medicine, actually got, maybe because they're more specific, so they got a higher score. That's a possible explanation. Now, what you want to see is the confusion matrix at this point, because how often did the classifier make a mistake by predicting the wrong category? We can see reflected in these numbers. So the numbers on the diagonal, we can make it a little bit bigger. See? The numbers on the diagonal, like 366, 392, 335, and 371, those are the largest numbers in the matrix, clearly. And those reflect the fact that when the predictions were made correctly, so when it's on the diagonal, that's the same row and column. So that means the true category was predicted correctly. Now, you can look and see which ones are the most confused. Now, you can see from this number 40 and this number 23 that very frequently the third category and the first category were confused. Now, let's look at which of those were. That's the first and the third. So that's hardware and electronics. So that's a little bit like we kind of predicted at the beginning, that since those two are very closely related, so there's going to be some confusion, and indeed there is between those subjects. And the other one that's a little bit it's less poor, but it's still perhaps significant, is the confusion between the third and fourth categories, which are electronics and medicine. You can understand that intuitively because there's electronic equipment involved in the medical practice constantly. So those are some pitfalls to be aware of if you want to make accurate predictions. Now, there's another trick we can do to fine-tune our predictions, and that is by using the following trick, using grid search. The grid search algorithm that sklearn provides allows us to fine-tune which parameters are the best for the algorithm in classifying the text. Then we can use that best one and use the results. So, for instance, we have, and all this training occurs on the training set. Before we apply it onto the testing set, we choose the optimal parameters using this grid search. And therefore, well, by the way, if you want to read more about grid search TV, so that is funny to read about it. And by the way, that's what the CV stands for, is cross-validation. Grid search CV, we're using cross-validation on the training set before we apply to the testing set. Now let's put it to work. So we're going to define the parameters, 3 of them. The vector n-gram range is going to be 1-to-1. That means it's just individual words, counts, and frequencies. And 1-to-2, meaning not only we're going to account for single occurrences of a word by itself, but we're going to take into account which word came next to it. So, for example, fastball, let's say if that's one word, but 2 grams or bigrams, like they're called, could be accounted for if we change n-gram range to be 1 up to 2. So, for example, I don't know, home team. or baseball stadium. So that would also be included. And the IDF that we discussed, that's the inverse document frequency, which tries to divide and eliminate the error due to the fact that some words are frequently occurring in a document, but they also occur frequently in all documents. So we can set that parameter to true or false if we want to account for that fact. And the classifier alpha, that's the learning rate. If we want to use 1/100th or 1/1000th, so sometimes a larger learning rate is better because it makes better corrections, but sometimes a smaller one is better because it doesn't overshoot when you're trying to correct for it. So let's put this into action by calling the following command. We're going to we're going to pass to grid search classifier, the optimal classifier. That's what we're making now, using the grid search cross-validate. And that is the text classifier that we have already. And we're going to choose the parameters that we defined above and cross-validate into 5 groups. That means we're going to divide our testing set into 5 separate groups and use each one as the testing set and the rest of it as the training set in order to practice before we get into the real world test. And the number of jobs will be -1. That we don't have to discuss for now. The result is going to be a optimized classifier that we can use. And let's type in the following. We're going to use GS, the grid search classifier, and we're going to fit, that's where the model learns, on the training set. We're going to only use first 400 samples just to make it a little bit quicker. And again, the target is the true labels for the categories. And that will be our trained model, grid search classifier that we call it. Next, we're going to calculate, after we trained it, we're going to see what's the best score. And let's do that on its own, for its own cell. What we get? The best score we got is actually 90%. Not as good as what we got before, 92%. And let's just see what we get when we run this. What are the best parameters that we got? Is the alpha is going to be 1/1000th. We're going to true. We are going to use the inverse document frequency. The n-gram range, we're not going to use bigrams. So we're just going to use words on their own. Now that you've optimized it, what the result is, we're just going to make up some examples here. My test sentences, I'm going to use this sentence. Bonds smashes wires, Sosa's record. And that'll be our test sentence. The category index array going to be, we'll continue this in another time at another opportunity. Thank you very much for watching.